All right. Well, I don't know who's on, but welcome to Office Hours for the Big Bang to Humankind. It's Andrew West here, and I am. Who's on? Oh, got a double there, making sure it was live. Um, so, what I'll be doing is monitoring the chat from both the YouTube, and I'll be also monitoring email. So if you have any questions whatsoever about astronomy or things we've been talking about in class, please send them to me, and I'll just be hanging out here for the next hour. Sorry that we had a few technical difficulties to start, but I think we should be fine now. All right, it looks like we got a comment from Sydney. I hope you're on, Sydney. And the comment is with the transit, or the question is with the transit method, and how are all these giants that pass in front of stars and briefly cover the light we can see from the Earth correct with a telescope? Where are we in relation to the star and planet? We are not in between, are we? Does it matter where we are in relation to the star planet, being closer to the star or being closer to the planet? It's a good question. So let me back up with that question. So with the transit method, basically you have a, let me see myself here, make sure I do this. You have the star, and then you have a planet that passes directly in front of it from our perspective. So it has to be perfectly aligned. Now, most of these stars, remember, even the closest star is, over 4 light years away. Most planets are measured in, astronomical units, much tinier fractions. So in all cases, we are much, much farther from both the planet and the star. So the planet is always much closer to that star. And that's why it actually doesn't matter the distance that the planet is from the star in terms of how much of a shadow or how much light it's going to block. All that matters geometrically is just how big the planet is compared to the star. And literally, if the planet were the same size as the star, which doesn't happen, it would block all of the light. And if the planet was half of the diameter of the star, that means it would have about a quarter of the area, and it would block a quarter of the light. Let me make sure. I think that answers Sydney's question pretty well here. Let's see. So transit method, how these planets that pass in front of the stars briefly cover the light we see from Earth. Where is it? We are in relation to the star and planet. Yeah, so we are not in between the star or the planet. We are much farther distance from the star and the planet passes between us and the star. It actually is orbiting the other star. It passes essentially right in front of us. One of the videos that I posted for this class on the page, or one of the links, I actually think it's one of the things I wanted you to watch before class on Thursday, actually shows a nice kind of demonstration of this. So I hope that helps. But the geometry, I think, to answer the question, what Sydney is really asking is the geometry is such that it doesn't matter how close the planet is to the star. Now that matters if we were much closer to the system, just like when Venus transits the sun, it actually matters that the Earth is pretty close to Venus. But in this case, the distances are so great that whether the planet is 1 AU or 2 AUs doesn't actually affect how much light it blocks at all. So I hope that answers your question. look forward to more. So I'm monitoring, let's see, I'm monitoring the YouTube chat, the current YouTube chat, not the original YouTube chat. Maybe I'll try to do the original one too, just to make sure. Let's see if there are any questions there. Are there any? Can I see the chat? Oh, I can just see Sydney's question. Okay, great. Oh, awesome. Oh, I see that. Oh, I see, Sydney, you made it to this one. I see your comments. Yeah, I'm hoping that those 8 people got my other email that said that there were some technical challenges. I actually started the chat on a different computer that was actually a larger screen, so that I could actually monitor the all the different chat windows. But for some reason, the camera wasn't working. I may have to actually restart the computer or something, and just so I could get here quickly, I just brought up my laptop. But Google and YouTube generated an extra link, a different link, so I had to pass that one on. So hopefully people see that. So, do you have any other questions, Sydney? Since I know you're on. All right, so Sydney has another question. Let's see. Since there are a lot of small stars, that means there are a lot of small planets. Correct? Yeah, that's right. So that graph I showed in class yesterday of it was basically a plot of the frequency of small planets around stars as a function of their, I think, temperature. But that could be also mass or size. And I hope what the takeaway that everyone saw was that small planets are more common around small stars or cooler stars, to be more accurate to that plot. There's 2 things that I think are really cool. First of all, the data used for that study are a little old. The way that this works is they're 5 years old or so, and so that plot hasn't changed qualitatively. It's still true that small planets are more common around small stars. What's actually changed is quantitatively. So before I fully answer the question, what's really cool is if you look at the y-axis, I guess, of that plot, you actually see that the rate is like a quarter of a star per or planet per star. And that seems funny because you can't have quarter planets, but it just meant at that time that it was showing us that, at least 1 out of every 4 stars have a planet of that size, which I remember seeing and thinking, just being totally blown away by that. I mean, the fact that, if you took all of those, that one type of M dwarf, M star, and a quarter of them, and remember, in our galaxy there are about 200 billion stars, at least 75% are M stars, at least 75%. So that's 150 million M stars at least. And if a quarter of them have small kind of terrestrial planets, at least a quarter, that says that, that means there's hundreds, or at least many tens of billions of stars. It actually turns out, in the last few years, we found out that there are actually probably at least 1, if not a few, small terrestrial like planets you could walk on around small stars. And that plot, of course, didn't take into account, which I think is where Sydney's question is going, didn't take into account at all that there are so many small stars in the galaxy. All it did is said, we just want to look at what the planet frequency is as a function of temperature. Then you put on top of that that almost all the stars in the galaxy are small stars. And it means that, there really are a lot of small planets out there, which is crazy exciting, and a really cool result. Other questions? I didn't see it. Didn't look like anyone else came over. Hope my second email went through. Yeah, okay, it did. So hopefully people will come over. But as of now, Sydney, the floor is yours. You can ask as many questions as you want until we get some more people on. Oh, awesome. Let's see. So, cool. We discussed that the Earth is small, so it's difficult to detect it, making the sun dimmer. That is more about the Earth being small in proportion to the sun, and less about it generally being small. Yeah, that's actually true. That's an awesome way of phrasing that. So Sydney's question is, that the Earth, we discussed the Earth being difficult to detect. It's actually technologically not, at least the Earth at 1 astronomical unit around a solar type star is not possible to detect from the radial velocity or the wobble method. We just don't have the technology to do that. We can actually detect Earths at much smaller distances, and that probably will be done around low mass stars very soon. There's a group at Yale University led by Professor Deborah Fisher, who's been developing some new spectrographs that are going to be sensitive, kind of like on the few centimeters per second level. They still won't actually be sensitive to Earths around suns, but they should be able to detect Earths around smaller stars. But Sydney's question really is about the transit method, and for the transit method, it really is the case that when I said the Earths are really hard to detect, it's because the Earth relative to the sun is so small. The Earth is about 1/100th the diameter or radius of the sun. And that means that the area that the Earth's kind of shadow would block is 1/10,000th of the area of the sun, because you take 100 and you square it, you get 1/10,000th. So that means when the Earth-sized planet passes in front of a sun-type size star, it only blocks 1/10,000th of the light. So you have to have a detector that is sensitive enough to be able to detect that tiny bit of a tiny break in the sun's light. That's right at the limit of our abilities. You can kind of do it, but not super well. But of course, if you took an Earth and you put it around a smaller star, so let's say you took the smallest or one of the smallest types of M dwarfs, which is now 10% of the size of the sun. So instead of the planet being 100 times smaller in terms of its radius, it's only 10 times smaller. And so it's going to block, again, 10 squared 100ths. It's going to block 1% of the light. And that's still a small amount. The star would dim by 1% if a Earth passed in front of it. But turns out that's a very easy thing to detect. In fact, could do that from a ground-based telescope at most colleges or universities, could do that kind of detection. So there is a kind of new effort to look for small planets around these really small stars. And in fact, there's a new NASA mission that I didn't have time to talk about that's called TESS. It's Transiting Exoplanet Explorer Satellite, maybe. I've got something exoplanet something satellite. But the point is, it's a telescope that's going up in space. It's not a very big telescope. It's going to look at nearby stars, mostly low mass stars, to look for mostly Earths. size things transiting. I mean, it'll find some bigger planets too, but the real goal is to find kind of Earth-sized planets orbiting probably mostly small stars. Cool. Awesome questions. Keep coming. Hopefully, some other people that were on will join us. Gonna look at my email really quick just to make sure I don't see anyone else. Just a moment. Nope, no other folks at this point. So still all yours, Sydney. You've got me to yourself. I hope a few more. Okay. Well, have a good rest of your day. I hope the others who were on weren't too thwarted by my technical difficulty. So thanks for your questions, and I guess I'll hang out and wait to see if some other people join. All right. I'm gonna mute it while I wait for more questions, and I'll look for them both in my email and in the Google chat. How do I? looks like that's about all the questions we have. Maybe we'll do this one more time. Um, and hope you guys have all a good weekend. All right, take care.